Okay, so I'm recording, and all you guys who are watching this goes along with my week 6 seminar on right here. I've got Jason online with me, so I'm going to go to a Webassign problem that illustrates something about what we call a z-score. So here's a situation. There are 430, let's say we looked at the heights. We did a survey. We took the heights of 430 NBA players and that were listed on team rosters at the start of the 2005-2006 season. So the heights of the basketball players have an approximate normal distribution with a mean of 79 inches and a standard deviation of 3.89 inches. All right, well, let's illustrate what that means first. I'm going to use the normal curve to try and describe what that means. All right. So when we say that there was a mean of 77 inches, well, that's a nice thick marker. I didn't need it that large here. All right, so we've got a mean of 77 inches here. All right, that's maybe a little better. What we're saying that is if we were to look at the distribution, make a histogram of the heights of our NBA players, we'd say, well, 77 inches would represent the middle of those heights. The standard deviation being 3.89 means that if we went 3.89 inches to the right of that 77-inch mark, so if I took 77 plus 3.89 inches, I would end up with 80.89 inches. That is, somebody who is one standard deviation to the right higher than the mean would have a height of 80.89 inches. Right? And by the same token, if I wanted to go one standard deviation below the mean, that would mean I'd have to take 77. Come on, pen. Sometimes my pen likes to cooperate with me, sometimes it doesn't. 77 minus 3.89 inches. And I'd have to calculate what that one was. And I guess it might help if I get my calculator out here. So let me get my calculator. So that means 77 minus 3.89 inches, and I get 73.11 inches. Yeah, 73.11 inches. Now, there's a rule that tells us essentially approximately approximately 68% of all the players in the NBA then will have had a height somewhere between 73.11 inches. Right? This is called an empirical rule. It's just based on that. If we multiplied our standard deviation times 2 and added to 77, or multiply that standard deviation by 2 and subtracted it from 77, we could actually find that approximately 95% of all of the basketball players in the NBA had heights between these two numbers, whatever they were. So if you take 2 times the standard deviation and go to the right, or you go 2 standard deviations to the left, right, you can tell how far away you are from the mean, and essentially, you know, what percentage of your NBA players would have heights between those numbers. So it's kind of interesting that when we say a mean of 77 inches and a standard deviation of 3.89 inches, what we really mean is that's a way of setting up an interval in which we can contain, well, some percentage of NBA players. All right. So let's say that we had a basketball player that had a height of 81 inches. Right? How many standard deviations away from the mean would he be? Well, this is where we use something called a z-score. A z-score goes like this. A z-score says take the value of whatever number it is, the value of your variable that you're interested in, subtract the mean, and take that difference and divide it by the standard deviation, right? So if I said, all right, I have a player who has a value of 81 inches. Well, that z-score tells me that if I take 81 and I subtract 77 and then divide that by 3.89, that's going to tell me how many standard deviations to the right or left of the mean I am. All right, so let me get my calculator out again right here and just do this. So I would take 81 minus 77 and get a result, so that's 4 inches. And I'm going to divide that by 3.89. And so my z-score right here is 1.03. I always give it to the nearest tenth. So 1.03 standard deviations above the mean. And I know it's positive that if that z-score is positive, I'm to the right, and if that z-score is negative, I'm to the left. So let me go to my problem right here. Here's the problem. It says, all right, for the following heights, let's calculate the z-score and the standard deviation. And oops, I made a mistake, didn't I, right here? Because the mean should be 79 inches, not 77 inches. So, oops, let me go back to my drawing right here. Let me just get a new one. So, the mean is actually 77 inches. And by the way, we use this Greek symbol mu, which looks like a U with a long tail. Mu. It's the sound a Greek cow makes. That's the way I remembered it, because, you know, a cow says moo, and this one has a tail. It's a Greek cow, so it says mu. All right, anyways, so 79 inches. Good Lord, 79 inches, right? So we're told that there's a player that's 77 inches. So right away, you know that that player has a height that's less than the mean. So what does that mean to us? Well, what we're going to have to do is we're going to have to figure out the z-score for this fellow. So what we're going to do is we're going to subtract, just like we said. If you want to get the z-score, the formula goes, oops, get a pen, Professor Peoples. The z-score is some x value from your distribution, from your variable, minus the mean divided by the standard deviation. The standard deviation is that little symbol on the bottom. So in this first case, I'm going to take 77 minus 79 and divide that by 3.89 to get this. So, bring up my calculator. Bump. I only want one. I'm going to take 77. I'm going to subtract 79. I get negative 2. I divide that by my standard deviation of 3.89. And so my standard deviation is negative 0.51. Again, round to the nearest hundredth. Negative 0.51. Right? So if this is one standard deviation to the left right here, our actual z-score right here for 77 is almost just a little bit more than halfway between 79 inches, which is the mean, and one standard deviation to the left. So we say at this position z equals negative 0.51. And so if I'm in Webassign, the way it's going to work right here is that I'm going to enter in a z-score of negative 0.51. 0.51, there we go. And applied who is shorter than or taller? Well, obviously shorter than the average. So let's do the same thing again, right? This time we're going to try it with the height of 85 inches and see what happens with it. So let me go back to my drawing right here. First of all, 85 inches, I can see right away, is a height that is somewhere above the mean right here. Maybe a little bit more to the right than 77, right? So 85 inches is way over here. To get its z-score, we should take 85 and subtract 79, which is the mean, and divide that by our standard deviation of 3.89. So let's see what's going to happen to that. 85 minus 79. So I get the number first, then I divide that by 3.89, and I see I get 1.54 when I round that to the nearest hundredth. So this is about 1.54. Since it's a positive number, that means it's obviously to the right, and this is the number that we're going to enter into our Webassign problem. Boy, I keep getting two calculators. That's interesting. So 1.54, and that's taller than the average. So finally, let's talk about this. Can we use that z-score if we know something about to find out something about somebody's height? Sure, right? 3.5 standard deviations is a z-score, right? And we say, well, what would that equate to as far as our height goes? And well, let's take a look at it. What does that mean to us? So let me open up my thing right here. All right, so we said 3.5 standard deviations. Well, what we say is this: when we're at the mean, we get 0. This is why z is equal to 0, right? This is why we call this a standard normal distribution. That is, 0 represents 0 distance from the mean. We're 1 standard deviation to the right of the mean, or 2 standard deviations to the right of the mean, or 3 standard deviations to the right of the mean. We could be -1 standard deviation to the left, -2, or -3 standard deviations to the left. So if I say I've got a z-score of 3.5, well, that's way up here. And we ask, well, what height would correspond to that, right? If the mean is 79 inches and the standard deviation is 3.89. All right, so what do? Well, remember, let's use our formula up here. But this time we're going to say, well, this time I know my z-score. I know that 3.5 inches would correspond to a z-score that's found by taking some value of the variable x minus the mean of 79 divided by 3.89. So here's what we're going to have to do. We're going to have to do a little bit of algebra. If I have an equation that contains a fraction, I have to multiply both sides of that fraction by the number in the denominator to clear the fraction. So that means in my calculator, I'm going to have to take 3.89 times 3.5 to give me 13.615. So that means 13.615 is equal to whatever x is minus 79. Now, using the algebra that we know right here, that means to us, I'm going to clear this up, that means that we're going to solve for x. And we're going to solve for x by adding 79 inches to both sides. Of course, that's going to give us x by itself, and that means we're going to have to go through and calculate 79 plus this number, So if I take this plus 79 inches, that gives me a height of 92.615 inches. So that's 92.615 inches. Now that's a pretty tall drink of water right there, 92.615 inches. So whoever this NBA player is, he's a pretty tall guy, right? So what would we say? Well, all right, we're going to enter a number, say round our decimal to 2 decimal places. So that would be 92. Gosh darn it, I have to go back here and look. 92.62 inches, right? So we're going to enter 92.62 inches. Let's see, there are few or many. Well, if we look at where this falls on the curve, it's way up here at the low end of the distribution, right? 3.5 standard deviations is well over here to this side of the curve. That's pretty far to the right. So what we say about it is that, well, there's got to be very few players who do that. So an NBA player this tall, so it is very unlikely that the player's Z-score is 3.5 and somebody must have made a mistake. Alright, so this is how that example works out right here. I'm going to pause. I'm going to stop my recording.